The other day, my daughter asked me to read her to sleep, and I said, just give me a minute. Like an hour later, I finished the problem I was on. I was like, oh, darn it, I missed out. You did your sheet? Oh, wow, look at that. That's nice. Excellent, excellent. Okay, so share screen. Okay. Yeah, I understand, busy. Okay. Just for fun, because it could be something more than just an x. It could be a 2x or a 4x or whatever. So just a slightly more general version of what's in the book. Couple of things to note here. It works out best if the x is located on the opposite side whenever possible. Otherwise, it ends up on the hypotenuse. Can you put it other places? Sure. It's just slightly different set of trig functions you have to work with, and they're not ones that are as familiar. And for me, my preferences are wherever possible. I like to work with sine, cosine, and tangent. When you're working with tangent, you have to work with secant, so that pops up a lot. So this is what is believed to be the most efficient set of trig substitutions right there. And so you could try to memorize these substitutions, or just some little tricks like the x usually ends up on the opposite side whenever possible. Otherwise, it ends up on the hypotenuse. Once you have that, you can write x equals or u equals pretty quickly and come up with what the square root's going to equal, and then your dx or your du. So we're just going to do a couple more examples of this today. And trig substitution, again, has been helpful in places where regular substitutions or integration by parts was not helpful. And this is just the same stuff in the book, but the book shows x's instead of u's. But if you wanted a trig substitution cheat sheet, this is it. All right, and I'll post that to the website too for everyone to see there. All right, so questions on the homework. So far, I've been asked about number 13 and number 14. Ooh, cute, cute, cute. Oh, yeah. Yeah. All right, so number 13 looked something like this. We were trying to find an antiderivative for, and let's not use red, please, yet, x cubed over 49x to the 8th. Oops, sorry, 49 plus x to the 8th in a square root in the denominator. And I always hate it when they put the dx in the numerator. It freaks me out. I like it off to the side. All right, so that makes me feel better like that. All right, so we need to come up with a substitution. Notice we have an addition problem here, which is going to put x on the hypotenuse instead of on a side. And then we have another complication. It's not an x squared there, it's an x to the 8th. And so it might help us to think about that as x to the 4th squared. And we could throw in a u substitution also. That might help too. Let's just try it without a u substitution and see what happens. I'm kind of curious. So this is theta. I like to label that. Makes me feel good, just like the dx off to the side. And then I'm going to put an x to the 4th. Sorry, I lied. The hypotenuse is the square root. The x to the 4th is over here on the opposite side. And then we're going to put the 49 as 7 squared, so this would be 7 here. And the Pythagorean theorem says that this should be the opposite side squared, x to the 8th, plus the adjacent side squared, 49, inside of a square root. So that's my triangle here. And what do I know about this triangle? Well, I know that the tangent is x to the fourth over 7. So that means x to the fourth must equal 7 times the tangent of theta. Do you remember, let's see, what's it called? Implicit differentiation? Okay, no, implicit differentiation is where we assume that, let's say the variable on this side is a function of another variable. In this case, it's a function of theta, which it really is here, right? Because it's equal to theta on the other side. So when we differentiate both sides, we just have to follow the chain rule, essentially. Well, let's see, do we actually need to do that here? Yeah, we do. Yeah, so, and yeah, this is a good thing to review. Implicitly differentiating x as a function of theta here, we get the derivative of x to the fourth, right, which is what? 4x cubed. And then, and we talked about this a while ago, and then what's the derivative of x with respect to theta? Well, it's just the derivative of x with respect to theta. Differentiating with respect to theta on the other side, we just get 7 and secant squared of theta. And this was what allowed us to do U substitutions earlier, way back in, gosh, when was that? Was that the end of chapter 5 or 6? It was a long time ago. And then we treat dx and d theta as actually differentials, not a whole quotient. And so that gives us 4x cubed dx equals 7 secant squared of theta d theta, which is going to help us in our substitution. And what else do we know? We know the cosine would be 7 over the, 7 over the square root, right? Or do I have that backwards? Cosine is adjacent over hypotenuse, right? Or we could say the secant is hypotenuse over adjacent, right? So that would give us here, switch back to black for a minute, that the square root of x to the 8th plus 49 is equal to 7 times the secant of theta. So those are all the pieces the triangle gives us that are going to be helpful in rewriting our crazy integral here. So let's see. No, because the secant is equal to the square root over 7. So I'm just bringing the 7 over to the other side. So it's just a secant there. All right, so what do we have here? We have an x cubed dx, which matches up there. We're just missing the 4. So we could divide that 4 to the other side. So I'm going to rewrite down here in red, say. So I'm going to rewrite this as the integral. Instead of x cubed dx, we're going to have 7/4. Let's leave a little room. 7/4 times the secant squared of theta d theta. And then, let's switch highlighters, about red. We've got our square root here, which happens to be right there. And so the square root can be replaced by 7 secant. So that's going to put that in the denominator. Let's see, red, yeah. So that'll give me a 1 over 7 secant of theta. Did I successfully replace everything? I replaced the square root with 7 secant, yeah. I replaced x cubed dx with 1/4 of that 7 secant squared. Yeah, I think I got all the pieces in there. Ooh, isn't that lovely? Stuff cleans up, the 7s go away, one of the secants goes away. All right, so let's put this on a new page, see if I can write it all correctly. Summarizing where we're at, we started off with the integral of x cubed over the square root of 49 plus x to the 8th dx. And we just rewrote that and cleaned it up a little bit. And I think what we have is what, a 1/4 secant of theta. Oops, wrong spot. Secant of theta d theta. Did I miss anything? Cancel the 7s. Secant goes into the square. Yeah, ooh, that's sweet. I love it when they fall apart like that. And then secant's one we've been seeing more and more often. That's the logarithm of the absolute value of the secant plus the tangent. So the antiderivative for this guy is going to be 1/4 of the natural logarithm of the absolute value of the secant of theta plus the tangent of theta. And then we have a plus c hanging out. And then we have to worry about reverse substituting. That says tangent, by the way. That's a little better. All right, so what do we know about secant and tangent backing up? If we divide this 7 over to this side, then the tangent is x to the 4th over 7. So let's switch back to blue. So this blue thing is going to be 1/4 natural log absolute value, and the tangent is, what did we say, x to the 4th over 7 plus, let's see, that square root is 7 secant, so the secant is the square root over 7. So then I'll have the square root of 49 plus x to the 8th over 7. And I don't see anything magical we can do with that. I think we're done. So another way to any questions on what I have here so far? Another way to handle the x to the 8th, if that freaks you out, is what we could have done is realize that's an even power there. We could have done a u substitution where we let u equal x to the 4th, and then we rewrite that before trig substitution. So sometimes problems are sufficiently complicated that you need to do multiple substitutions to get it down to something that you can see. So if I did that route here, note that du would be 4x cubed dx, right? Which I have dx cubed there. So I could have rewritten this as the integral of a 1/4 would pop out because we're missing the 1/4 there. And x cubed dx is just du. So I would get a 1 over the square root of 49 plus u squared. And then you could do trig substitution on that. After you're done with the trig substitution, you could then back up and reverse substitute for x. Yep. Yeah. Yeah. They got rid of the denominator? Yeah, so you could get rid of the denominator, I think, right? Yeah, properties of logarithms. So what you would do to get rid of, and I don't think it would mark you wrong if you typed it in this way. I'm pretty sure it would not. But if you wanted to get rid of it, so we have 1/4 times the natural log of the absolute value. Now, both of those fractions had a 1/7 in it, right? So we could essentially factor out the 1/7, and we would have 1/7 times parentheses, the square root of, what was it, 49 plus x to the 8th, and then was it plus x to the 4th? Close, close, plus c. And then property of logarithm says that if you have the log of a product, you can break that up as the sum of the logs. And so then this would become 1/4 times the natural log of 1/7 plus 1/4 times the natural log of that square root plus, and let's see, 49, oops, plus x to the 8th. And we could take this even further because the log of a quotient would be the difference of the log. So, or what else could you do? You could rewrite that as 7 to the negative 1, and it would come out as what, a negative 1/4 times the natural log of 7. And you could kind of screw around with properties and logs for a while, but I don't think you're going to get much better than that. The 1/4 could go in there as a root or a power, but I don't think I would want to do that either. Oops, plus x to the 8th. Does that kind of address, or you have another question? They didn't have any constants? Interesting. So one of us is wrong because I don't think these are equal. Oh, wait a minute.
I just wrote, like, I'm not sure this is
okay. This is what they claim the answer was, and they just had a 1/2 out there.
Mm-hmm.
Oh, because they have a different power, right? So it'd be a 1/2 instead of a 1/4, yeah. But they lost that. Okay, ooh, wow. So either I have a mistake or they have a mistake. So, all right, so they say the online homework doesn't like that. All right, so did I miss a constant in my substitution here? So let's just go back and review this. I let's see, 49 plus x to the 8th. So if we let this be x to the 4th, that's got to be 7. 7 squared is 49. X to the 4th squared is x to the 8th. Tangent equals x to the 4th over 7. So x to the 4th has got to be 7 tangent. Which we never used directly. We just used that one and that one. So is there a mistake in either of those lines? Derivative of x to the 4th is 4x cubed. Derivative of the tangent, secant squared, the 7 sticks around. We can't get rid of that. Let me see what they wrote again. They wrote, well, I still have the 49 there. Oh, this one down here. Interesting. I don't see an error here. You guys see any constants I'm missing? Let's see. Oh, interesting. They don't list it here either in the answer key. The secant is the square root over 7. Yeah. Repeat that, Stanton. Sorry.
So when you took the derivative of the 4x and the 7 tangent, you put in the dx over d theta. You need to put in d theta over dx.
No, because we're taking the derivative with respect to theta. So on the other side here, the chain rule would say you need the derivative of theta with respect to theta, which is just 1. Because on both sides, I'm differentiating with respect to theta was the key there. Yeah, so that's all right. I don't see it. And then we did our substitution and cleaned it up, and those 7s did cancel. Reverse substituting. I don't know, I'll think about it some more, see if I can find. Because often when you're playing around with trig functions, you'll get 2 slightly different looking antiderivatives, but if you set them equal and solve, you'll just find they're different by a constant. So it could be there's a value. Oh shit, yes, that's it. Duh, it's right here. Here's the different by a constant. Yeah, any two antiderivatives have to be no more than a constant difference. Well, the online homework claimed the answer was just this part right here. This is the difference of a constant, which they could suck into that C there and call it K instead. So if I combine this guy with that guy, we could call that new constant K. So then my answer would be 1/4 times the natural log, absolute value of all this stuff, plus K. What's K? Well, it's some constant related to that number right there. Yeah. But I'll have to go look at, they probably showed a step-by-step method for doing this. So somewhere in their step-by-step method, they found another way to get rid of the 1/7 earlier. So I'll have to look at that and see what they did. Yeah. Okay, so this answer is correct, whether you write it in this form or that form. They're all the same thing, different by a constant. So we're okay. Well, that was fun. Whew, I'm glad we solved that mystery. Yeah. No, I'm not. Actually, usually the authors of those problems are pretty good at writing the programs to consider things like that. So if you believe you have a correct answer that it doesn't like, just hit message my instructor in there. It's right below the show me an example and say, hey, this is what I got. I think I'm right. I think it's the same as theirs. And sometimes it's easy to find that constant difference. Sometimes it's not. Sometimes it's a lot of work. But we accidentally found it right there. Just playing around. Okay, let's do another. So the next question was on number 14, which is find the area in the first quadrant bounded by the coordinate axis and the graph of. So we need to consider y equals something like 9 minus x squared inner roots divided by 7. Okay, so that is not a semicircle, is it? Or an ellipse? Let's see, if we rewrite this as 7y equals the square root of 9 minus x squared, and we square both sides, we get 49y squared equals 9 minus x squared. And so adding the x squared over, we get 49y squared minus x squared equals 9. It is an ellipse. Plus, oh yes, plus, sorry, that would be a hyperbola. Yeah, it's an ellipse. And let's see, if we rewrite that, what would I have to do to rewrite it? I would have to divide everything by 9. So that would be 49y squared over 9 plus x squared over 9 equals 1. And these constants tell me what the axes of the ellipse are. So according to those constants, the x-axis should branch out to -3 and 3. So we'll have points here and here. So I'm just trying to get a graph without the calculator. If you guys have calculators, I highly recommend whipping them out and getting a graph of this thing up here. And then the y-axis would be, let's see, if I take the reciprocal of that, that would be 9 over 49, which is 3/7 squared. So if this is 1 right here, 3/7 is like right there. So this should be an ellipse shaped like that. We've got y equals the positive square root, which means we just want that top part of the ellipse. In the first quadrant, so back that up. Ooh, I can't back that up, can I? I drew over my line. Undo. So they said to just look in the first quadrant, so we're looking to calculate this area right there. All right, did anyone check if I got that graph right? That's the right one? Yeah. So yeah, the y equals, that's the positive square root. Underneath would be the negative square root. Yeah. So I'm just going to bring it up on GeoGebra 2 just for fun. Or let's use Desmos. I haven't used Desmos in forever. Right, so we want y equals the SQRT of, was it 49 plus x squared? No, minus x squared. Oops. So that would be a circle. Once we divide it by 7, we turn it into an ellipse. Oh, 9, sorry. Oh, there we go. Okay. And so that right there should be my 3/7 right there. That doesn't look like 3/7. No, I thought it was going to be actually 3/7. 778 is not 3/7. Did I get the numbers wrong? There's 9 up here. That's the 9, and 49, or 7's down here. Okay, so then 4, 2, 8, 7. Yeah, that's right. Okay. Yep. Thank you. All right, so we're trying to find the area in here. So I can't remember, does Desmos do area? It doesn't? Does it do integrals? Oh, look at that. So we want the integral from 0 to 3 of, so we can cheat and get an answer, the SQRT of 9 minus x squared over 7. And I think I just type it like that. Ooh, it didn't like that. Does it need a dx? Ah, yeah. Okay, so Desmos says it's around 1. Let's see if we get 1. All right, substitution time. So we are trying to find the integral. Ooh, it's a cute integral. Amazing, I was feeling so bad before class, and all this math made me feel so much better. Does that happen to you guys too? No, it's the reverse. Oh, that's still not a pen. Shh. Okay, so I want the integral of the square root of 9 minus x squared over 7 with respect to x. 1/7 is just a constant. We can pull that out, right? So we'll consider 1/7. So anytime we can clean up the integral so we don't have to mess with stuff, the better. All right, so trig substitution. Theta right there. Let's see, we want that x to go over here. And then the 3 has to be the hypotenuse, because then this side will be the hypotenuse squared minus the other side squared inside of a square root. So there's our 9 minus x squared. So let's see, sine is x over 3, so x is equal to the 3 sine of x. Dx, I usually grab that right away, would just be 3 cosine of x. Dx. And the square root over 3 is the cosine, right? Cosine's adjacent over hypotenuse, so that means my square root of 9 minus x squared has to be 3 cosine. Oops, no d thetas here. We already did that part. Okay. So remember, usually the variable is going to go on the opposite side or the hypotenuse, and then we figure out where the other two things go using the Pythagorean theorem. Then I like to write down what x equals, then dx, and then what's the square root according to the trig functions. Then we just go back and plug in and see what happens. So let's rewrite this in blue. So what do we get? The 1/7 is still chilling out front. The square root is 3 cosine. And dx is also a 3 cosine. Oh, we've done this one before. I mean, cosine squared at least. D theta, right? Oops, something's wrong here. Oh, these guys should be thetas. Thetas. Oops. Okay, that's better. All right, so it looks like we have to then, we can pull out that 9. So we have 9/7 integral of the cosine squared of theta. And what's our best friend with respect to cosine squared? It's the, well, no, it's either the half angle formula or the double angle formula, depending on your perspective on that. Okay. And so that means this is going to be equal to, we still have our 9/7. The half angle says the cosine squared is equal to 1 plus cosine of 2 theta all over 2. So that dividing by 2 is a factor of 1/2, right? So I'm going to get 9/14. And then antiderivative for 1, just be theta, right? And antiderivative for cosine, well, that would be the sine, but that 2 is messing me up there. What's going to happen with that 2? Yeah, it's going to be a plus 1/2 sine of 2 theta. And I don't have boundaries in here at the moment, so let's see. If we were going to do boundaries, or should I reverse substitute? I don't know. What were our boundaries supposed to be? From 0 to 3? So x is going from 0 to 3. Okay, so if x is 0, what must theta be? 0. Okay, so that's good. We can keep our 0 boundary. And then if x is 3, then we get 3 equals 3 sine theta. Which is 1 equals sine theta. When is the sine of theta equal to 1? Pi over 2? Or negative pi over 2? Yeah, so we're going to go with pi over 2. Oops, it's in the direction we want to go. So pi over 2. So I could have reverse substituted, but that felt like more work. Calculating the boundaries seemed easier here. All right, so let's see. We've got 9/14 times, oops, that was rather sloppy, pi over 2. What was next? Plus 1/2 the sine of 2 times pi over 2. Oops, premature on the boundary. Let's see. Yep. And then we're going to have to subtract. Oops, pen. Let's see, we're plugging in 0, so theta is 0 plus 1/2 sine of 0. All right, so let's see, what's the sine of pi? Yeah, so this is a 0, and that's 0, this is 0 also. So the only things left are the 9/14 and the pi over 2. So that would be what, 9 pi over 28? Let's see, 9 times 3 is about 27-ish, a little bigger, or maybe almost probably bigger than 28, which is about 1, which is what Desmos said. So I'm just going to calculate that number to double check that it's a little over 1. Desmos, what is 9 times pi over 28? Desmos said it is the same as before. Woohoo! Party time, we did it. That was fun. Ooh, wow, that's quite the calculator. What does that mean? Oh, yeah. So, yeah.
You can see it on the...
Yeah, so whatever that y value is that's the 1.0 something, yeah. Yeah, cool. That's a sweet calculator. How much is that one? Your sister gave it to you? Score. Okay, so should we do another one? Do we have time? I think we do. Okay. I thought number 8 was cute, unless somebody has another problem they want to look at.
I like number 8.
You like number 8? You haven't even looked at the homework yet. Okay. What else was I thought was cute? What's 39? Which one is that one like? Number 12 was cute. All right, what do you think? 8 or 12? 8 it is. Okay, so my number 8 looked like this. It was the integral of x cubed over x squared plus 121 in the square root. I get that right? Yeah. With respect to x. All right, so first step, we build our triangle. Now, often, I mean, this section's about trig substitution, so we're diving right into trig substitution all the time. But I usually pause and ask myself, can I do this with an easier method? Because trig substitution is cool, but it's kind of complicated. Like, would a regular substitution work? Like, if I let u equal x squared plus 121, would that deal with my numerator here? Not really. It might work, might not. Interesting thing, if u equals x squared plus 121, so I just want to play with this for a second, because it's always worth saying, hey, is there another way? So just note, if u equals x squared plus 121, then du would be 2x dx. Well, I have an x up there, but I also have an x squared sitting next to it. But I know that x squared could be u minus 121. So it could be that substitution might work if we took it a little farther. So my guess is maybe this substitution with an integration by parts might do this too. But we tried an integration by parts the other day and get stuck in an infinite loop. So maybe not. You never know till you try. All right. So I'm not going to do that regular substitution, although I think it has potential. So we're going to do a trig substitution. All right, so theta is here. Let's see, since there's a plus here, that means the square root has to be along the diagonal, x squared plus 121. We generally like to put the x to the right side whenever possible, which forces the square root of 121 to go on the adjacent side. So I usually think about where should the square root go and then where should x go? And usually I want x to go on the hypotenuse or the opposite side of the angle. All right, once I have that, I start writing down what I know. So let's see, x over 11 would be tangent. So x must be 11 times the tangent of theta. And what else? Dx would then be 11, secant squared. D theta. And the square root over 11 would be the secant. So the square root of x squared plus 121 should be 11 times the secant of theta. Let's see, so I see my square root there. The x cubed is a little troublesome, but can't I just cube this top equation right there? So I could say x cubed would be 11 cubed times the tangent cubed of theta. We'll see. We might get lucky and stuff will start disintegrating once we plug it in. It's possible. All right, so plugging stuff in, our x cubed is 11 cubed times the tangent cubed of theta. Our square root is 11 secant of theta. And our dx is 11 secant squared of theta d theta. Did I get everything? Got my x cubed, check. Got my square root, check. Got my dx, check. All right. Partially, yeah, we get a little cancellation. Let's see, what should we cancel with? Red. We get one secant out of the way. We get a pair of 11s out of the way. So we have 11 cubed, tangent cube, secant. Okay. So now we've got, we'll throw the 11 cubed outside. And what was it? Secant cubed tangent or tangent cubed secant? Thank you. Tangent cubed of theta times the secant of theta d theta. Okay, so let's see, what can we do here? Looks like we're gonna have to go with either a trig identity or integration by parts or some kind of u substitution. So what do we know? That if we take the derivative of the tangent, we get secant squared, that's not there. Derivative of secant is secant tangent, that's not there. Oh, we do, I'm thinking maybe integration by parts on this. Rewriting it as tangent squared of theta times tangent secant. Let's see, so that's one option, because this thing right here makes a nice dv, doesn't it? Alternatively, let's see, what's the trig identity for tangent and secant? Can never keep that one straight. Is it tangent equals 1 plus secant squared or vice versa? Tangent squared equals 1 plus secant squared? There we go. Trig identities, SOS. 1 plus tangent squared is the secant squared. So secant squared would be tangent squared minus 1. Sure. So if we rewrote, so just brainstorming. Oops, I didn't want to undo that. Wrong button. Want my colors. Okay. So let's see, what did we discover? This thing right there as an identity would be secant squared minus 1. Is that right? Secant squared of theta minus 1. So that, or other option, let that be dv and integration by parts. So let's see, if we make that a secant squared minus 1, we get a secant tangent, and then we get a secant cube tangent. Ooh, man, that's promising. Integral of the c. Oh yeah, I think I like this. Yeah, I think I'm leaning toward that. So write it down, let's see what happens. So that's gonna give us 11 cubed times the integral, and I'm gonna have to just distribute this blue thing to the red thing. So that's going to give me a secant squared of theta times this blue secant tangent. And then minus just that secant tangent. D theta, did I get that right? We distribute secant tangent to secant squared and to -1, yeah. And then here, what's the derivative of the secant? It is secant tangent. So this sucker right here, we have hidden in here, this would be u squared du, u squared du. And then over here is the derivative of the secant. So what's the antiderivative of secant tangent? It's just secant. Yeah. So then I'm kind of skipping a couple of steps because we are just about out of time. My belief is the 11 cubed we're stuck with. The antiderivative of this fourth part would be u to the third over 3. And my u is a secant here. Okay, u secant. So I think I've got 1/3 secant cubed of theta minus the antiderivative of secant tangent is just secant. And then now it's just a matter of reverse substituting on that based on our triangle, which I think we have enough time to do. Yeah, we got a couple of minutes. All right, so we've got 11 cubed. Let's switch colors again. 11 cubed, oops. And is the only constant, the 1/3 is only part of that one. Okay, so I can't pull anything out, sort of. 11 cubed times 1/3 secant cubed of theta minus, sorry, secant. And our substitution says secant is the square root over 11. And I guess that's all I need to know. Okay. So back here, we're going to get, switch to black. We still have that 11 cubed hanging out front. I think that's going to clean up in just a moment. And then 1/3. So let's see, the square root, let's consider that the 1/2 power. 1/2 power to the third power would be the 3/2 power. So then I'll have, what was inside that sucker anyway? X squared plus 121. All right. So we'll have an x squared plus 121 to the 3/2 minus, oh, I'm missing something, over 11. So the 11 is going to get cubed, so that's going to be over 11 cubed, minus secant, which is, I guess I'm going to write it as x squared plus 121 to the 1/2 over 11. And I guess we could multiply that 11 cubed 3 and clean it up just a little bit. Or we could factor out an 11. Either way, I don't know which one uses less ink. It's about the same in my opinion. So maybe I'll just go one step farther. If I distribute the 11 cubed, then we would just have 1/3 of x squared plus 121 to the power 3/2 minus, we get to get rid of one of those 11s, so 11 squared times that to the square root or to the power 1/2, whichever you prefer. And I don't think we can do much better than that. We could factor out a square root, but I don't see how that helps really. Oh, yeah, if we factored out a square root here and here, then we could turn the remaining part into a polynomial, but it's kind of an ugly polynomial. So I think I would just stop there. No, can we take one more minute? Do you have trouble with one more minute? Okay, we'll stop there. All right, that was fun. So do your homework. Yeah, lunch is a good idea. All right, do your homework and let me know if you have any questions. We'll do more fun math tomorrow. Really? I didn't know that.